Hi, this lecture is going to be the second color vision system that was developed back then. Okay, this is CRE color specification system, which is actually further developed to the proper color system, and whatever that color that we able to produce now, or with whatever photography technology advancement that we have, the basic foundation for the colors is actually come from the CRE system. Okay, so we're going to look at how this CRE system is actually developed, okay, step by step. So color matching is the process of reproducing a specific color by combining different light sources in controlled proportion. So this is the idea that is actually used by the CRE color system developer, okay, where they actually, try to use the red light, green light, and also blue light to mix the lights and to produce all the colors that can be found in the visible spectrum from 400 nanometer to 700 nanometer, 400, 401, 402. So they produce every single colors in that range, okay, using this process, the color matching process. So the color matching aims to achieve a perceptual match between a reference color and a mixture of primary colors. Okay, so what they did is they have, gotten all the colors. For example, they put a 400 nanometer colors, okay, at the top. And then, subjects, there were many subjects that involved in this experiment where what they have to do is they are provided with they are provided with 3 lights colors, okay. So based on the top one, they have to actually, and then they have a bottom one where a color that is actually produced by mixing all these 3 lights will be shown that. Okay, so what they have to do is they have to adjust this red light, green light, and blue light to match the colors at the top. Okay, so they did the same for 402 nanometer, 403, and throughout all the visible spectrum. Okay, so this is how this CRE color system, the foundation of the research started from. So basically, the subjects were given 3 light colors, red, green, and blue, and then they have to match the colors of all the colors in the visible spectrum. Okay, so basically that is what was done, and the good thing is this color system, which was developed through the through this experiment, okay, is currently widely used in various industries such as printing, photography, textiles, and digital displays to ensure color consistency and accuracy. Okay, so the first system that was developed, okay, the experiment was conducted, and then they come out with the first system. Okay, so the system is actually named as RGB. It stands for red, green, and blue system. Okay, and it is the 3 primary colors used in additive color mixing system. So in the experiment, these are the 3 colors used to indicate the 3 types of cones that we have. Okay, so in additive color mixing, different intensity of red, green, and blue lights are combined to produce a wide range of colors. So these red, green, and blue are considered primary colors in the RGB systems because they cannot be created by mixing with other colors. They are pure colors. Okay, and each primary color has a specific wavelength associated with the red to be about 645 nanometer, green about 522 nanometer, and blue is the shorter wavelength about 444 nanometer. So in the RGB system, the colors are created by varying the intensity of red, green, and blue light. Okay, so mixing all these primary colors at full intensities produce white light, while absence of all these 3 is producing a black light. So basically, when you combine all these red, green, and blue, okay, together, okay, in full intensity, it will produce a white color. But when you adjust the intensity, then you can actually, match all the colors in the visible spectrum here. Okay, so that is the basic idea. Okay, when you actually remove all these lights, these three colors, then you will produce a black color. Okay, so basically this RGB system, okay, they started off using the three lights. Okay, and also these three lights is the intensity of the lights is actually matched. Okay, the wavelength is maintained to be, as per, the one I mentioned, 645, 526, and also 444 nanometer. The intensity is the one that is actually, adjusted to actually matches the color. So if we look at this, right, this is how it looks like. So this is the color that is, changed, from 400, 401, 402, 403, until 700. And this is the column where when we mix, okay, this red, green, and blue, it will be shown here. So once these two are matched, then it is actually stopped. And the reading of the intensity of red, green, and blue is taken, and then they produce this graph over here. Okay. Okay. So when this system, RGB system, is widely used, okay, once it's already, the investigation is done, so they actually, try to use it, whether it works or not. Okay, but it was found that they have a limitation while using it as a system. Okay, in accurately reproducing certain colors, especially in this zone, about 450 to 500 nanometers. There is an issue in reproducing these colors because we don't have like a proper value for it. Okay, the negative amounts of primary colors may be required in certain regions of the spectrum, leading to challenges in achieving precise color matches. Okay, so basically what is plotted here is, if let's say I want to match, okay, about 650 nanometer, about 600, okay, maybe I can say that about 805, okay, nanometer, sorry, 605 nanometers around here. So how much of red is needed is, the intensity is about 3 that is needed for red color, mixed with about, 0.1 of green and 0 blue color. Okay, 0 intensity of blue color will produce this 605 nanometer colors. So it is plotted that way. So once they already, mix and then it matches, then they record down the value. So that is what is being plotted. So the funny part here is the negative portion. For example, if let's say I want to match about, 450 nanometer. Okay, it's about 0.5 of green, 0.5 intensity of green, and also 0.5 intensity of blue is needed, with a mixture of minus 0.5 of red. Okay, it doesn't make sense. How can you mix a minus 0.5? Okay, so that is a question that is running. How can these people, create a system and then they have like a minus? Okay, so this minus is like a drawback. So when, when they present it to, to get approval, okay, after they run sometimes, then they want to get approval to make it, official. So when they want to actually make it official, so what happened is when they presented, people query them, how can you have a negative, portion over there? And then it was explained that, okay, in this range, about 450 nanometer to about 520 nanometer, okay, how much, they have tried different way of, try to increase red, decrease green, try to increase blue, put it in an intermediate value, but still they cannot match, any colors in that range. Okay, so it has been constantly happening to all the subjects. So what happened is, what they did is they tried to actually mix the red light to the target that they have given. Okay, they mix the red light to this target, and then a new color is produced, and then they use the blue and yellow, blue and green to mix and match this color, which doesn't make sense, obviously. Okay, which doesn't make sense at all. And then, but it is accepted at that point of time. They say that, okay, your color system looks good, but we want you to rectify this to see whether you can actually, if you're able to rectify this, then we can approve you your system as the proper one. So what they did is So these people, these researchers brought back, their presentation, and then they think of how can we make, this color system graph looks proper. Okay, so what they did is, rather than presenting the, okay, it doesn't make sense anyway. Okay, they say that rather than presenting it in a number value, okay, why don't we present this in a vector component? Because when you present this in a mathematical way, in vector component has no minus value. Okay, they have like x portion, y portion, and they have z portion. So when they have three, all the values in the negative will become positive in the graph. Okay, so the CIE system, which is this XYZ system, is actually, they address the limitation from the RGB system. Okay, so they transform the RGB system to XYZ system by changing their values to vector component. Okay, so that vector component make them to have all the values to be positive. When it becomes positive, okay, so this x, y, z are imaginary primaries defined by the system. Okay, this is an imaginary primaries. It is no more the true colors as it was in the RGB system. Okay, so it was not a true primaries, they are imaginary primaries. Okay, and then they're able to transfer this minus value to, positive value. Okay, and then they went and presented to the same team, and the team accepted their presentation, and they said, okay, now we give you approval, so please do develop this further to color vision system. Okay, that is known to be CIE in after that. Okay, a proper color vision system so that people can identify colors easily. Okay, no, obviously you cannot stay in a graph form anymore, so there should be a proper system. So further refinement is actually conducted. At the end, it comes with a CIE system. Okay, if you ask me logically, how can they just use vector component? It is not logical. Okay, but if let's say you are able, when you do a research, you're able to actually convince your, panels, then that's it. Okay, so all the theories are like that. So if you're able to actually convince the, the panel who is actually in the board of, approval, so then you can actually proceed with anything. So this CI system is also like that. So I have been looking for many papers on how do they can actually accept this, because practically doesn't seem to be making any sense. Okay, but then it is actually developed, and so far we have no issues in identifying colors. When we want to recreate colors, we don't have any issues with this visual system. Okay, so that should be a convincing part. Okay, but when looking back at the theory, it doesn't make sense. But when you use this CIE system to develop colors, to reproduce colors, it is actually producing similar colors. Anyway, okay, so looking at output, it is actually acceptable. But looking at theory, it is not actually very convincing. Okay, so this X, Y, Z tri-stimulus value are further transferred into CIE color matching functions for three real primaries: red, green, and blue. Okay, so this transformation involves mathematical operations, converting into vector components and all that. So they further develop all this into a CIE diagram like this. Okay, so there are many steps that is involved, but for your stage, you don't need to go deep into this because we are not into that. Our job as an optometrist is to diagnose them and then provide them a proper management. So you just need to know how this, light are being perceived, how they have actually developed a, color vision theory, how that actually, converted into a visual system. Okay, that's all you need to know. So I have actually skipped that, okay, because there are more important things that you need to learn. Okay. So now, move to the next slide. Okay, unlike the imaginary primaries in the XYZ system, CIE color matching function use real primaries to represent actual spectral colors. So these real primaries correspond to spectral sensitivities of the human visual system, providing a more accurate representation of color perception. So when they converted the XYZ to CIE diagram, so they take into consideration of the taking the real primaries, the red, green, blue, rather than the XYZ system. So they use the base of XYZ system, but then when they actually made this CIE chromaticity diagram, they have actually used the real colors value to form this particular diagram. Okay. And the CIE color matching functions are standardized representations of human color vision, ensuring consistency and precision in color reproduction. So they are, because they are using the real primary colors values, so they are very accurate and consistent in actually producing colors. So they serve as a basic for various color spaces, models, standards used in industries such as photography, printing, and display technology. Okay, since they use the real primary colors and they are already arranged in a very proper manner, so they are actually very, this particular CIE system is actually very precise and consistent in producing the colors. Okay. Okay, now we look at the basic attributes of the CIE chromaticity diagram. Certain things that you have to know is, so this is the monochromatic hues, okay, starting from 400 nanometers, okay, it goes to 520, you know, if you see 400 is about the blue color, and then it changes to green color about 500 nanometer, and then when it reaches about 600, you know, to 700, it is goes to the red shades. So it is the, you know, the same thing, 400 to 700 nanometer, that one that we see in the visible spectrum, just that it is in a different shape. Okay, so it is actually arranged along arc of the perimeter of the diagram, okay, which is referred to be the spectral locus. So this line from dot here and all the lines up to the 700 nanometer is known to be the spectral locus. It is a monochromatic light. Okay, so the non-spectral purples fall along the straight line between these 300. Okay, this is the, okay, the connection that is you know, human made, so that we can have all the real colors inside this leaf like you know, diagram, and whatever that falls outside are all the imaginary colors. We don't see the colors. Okay, so whatever that falls into this, so this is the one that we see monochromatic light. So these are all the mixtures of all colors. Okay, this one could be like a mixture of, you know, blue and green. This one is like green and yellow. So it's a mixture. All whatever that's inside is a mixture. So mixture of all colors falls here. Okay, when mixture of all colors fall here, and mixture of all color is always white. Okay, if you still remember, okay, when you learn about you know, rainbow. Okay, so when there is a white light shine to a prism, okay, this prism has the capability of actually, you know, disperse all the colors that constitutes the white color, and it is always found that it actually stands with the rainbow colors. Okay, so this rainbow, each of these rainbow colors are monochromatic, while this white color is a polychromatic. It's a combination of all colors. Okay, so this is particularly made so that all the colors inside are the visible colors. So whatever that falls outside are the imaginary colors. So that is the CIE diagram. So it started from RGB system, matching three lights to, you know, mixing all three lights to match the colors on the visible spectrum. And they found that there is a negative portion because there is a one range of colors cannot be mixed with any options. Okay, mixing with any you know, combination doesn't, you know, match the colors. So they shine the red light that is used to mix, they shine it to the targeted light, and then it produces new color, and then the new color is matched with the remaining red and green light. And when they presented, it was found that that doesn't make sense. So they were actually, went back to repair that and come with XYZ system. So, but this XYZ system, how did they actually, change from RGB to XYZ system is they have actually made the XYZ system by actually changing the value of this red light, intensity, green light and blue light intensity to a vector component so that they can remove the minus value, the negative portion. So once they have actually converted to the component, so all the value is in the positive portion. There is nothing in the negative portion. However, and it got approved. However, okay, this they are imaginary colors X, Y, Z. So when they actually further develop the proper color vision system using a CRE diagram, it was found that with the imaginary colors, they can't actually make a proper CRE diagram chromaticity. So they actually, use some other methods to actually convert back to the real primary colors, and they came out with a proper, color vision system through this CRE diagram. Okay, so that's how the color vision is actually developed. So with the color vision system that is developed, that's when this color vision system is actually, used in the industry to reproduce color, to actually, in many industry, and also even in optometry also we use this color vision system to actually invent, television tests and all that so that we can diagnose them. So with the system, only be able to produce reproduce the, the diagnostic tool in a more systematic way. So that is how the color vision system is actually developed. Thank you.